Welcome back to Statistics. It's Wednesday, April 22nd, and today we're going to talk about the last major topic in our course, +4 confidence intervals for proportions. So last time we talked about the basics of confidence intervals for proportions and went through the process there. And you may have noticed that in all our examples, the sample size was pretty large, and that's not an accident. The techniques we talked about in the last video are designed for large samples, and they work well for large samples. But when the sample size gets very small, those techniques become less accurate. And so we need some method of doing confidence intervals for proportions when the sample size is small. And the so-called +4 methods that we'll talk about today provide just exactly that. So let's remember what the basics of confidence intervals for proportions consist of. The level C confidence interval for a proportion P is the sample proportion, P hat, plus or minus a margin of error that's calculated this way, a critical value times that standard error, which is the expression in the square root. Now, you may have noticed that the book refers to this as the large sample confidence interval, and that's because of what I just mentioned. It is designed for large samples. But when the sample size gets small, say especially sample size is less than 20 or so, then this interval becomes less accurate. And let me show you what I mean here. I ran a little simulation in which I basically took repeated confidence intervals from a population where the true population proportion was a half. And so I just took random samples repeatedly of size 15 here, and for each random sample I computed a 95% confidence interval. And then I colored the confidence interval green if it actually contained the true proportion of a half, and red if it didn't. So we've seen these kind of simulations before. This was a 95% confidence interval, so we expect that about 95% of 95% confidence intervals will contain the true proportion, right? So we'd expect 95% of these 200 confidence intervals that I simulated here to contain the true sample proportion of a half. But as it turns out, only 89% do. And that's related to the fact that the sample size here is so small. For small sample sizes, the large sample techniques that we talked about previously just aren't that accurate. But fortunately, there's a simple fix for this. It's called the +4 confidence interval. And I'll tell you more about what that means just in a second, but let me just show you the results. Here, I reran the simulation. Again, 200 confidence intervals were calculated, and I checked to see which ones of them actually contained the true proportion of p equal a half. And it turned out that all but 8 out of these 200 did. That gives us an overall hit rate of 96%, which is a lot more like we would expect for a 95% confidence interval. Remember, we expect 95% on average of 95% confidence intervals to contain the true proportion. And here, in 200 tries, 96% of them did. So that sounds a lot more reasonable. These confidence intervals were computed using the +4 method, which is a slight modification to the large sample methods. And the +4 method is the preferred technique when your sample size is small. So what is the +4 method? Well, the +4 confidence interval for a population proportion P is really a very simple modification to the large sample method. You're going to basically add 4 imaginary observations to the data set. 2 of those will be successes, and 2 of those will be failures. And so then you just do the large sample computation based on this augmented data set. So the sample proportion of successes, which I'm calling P tilde now to contrast it with P hat, would be the number of successes, including the two new imaginary ones, divided by the sample size, including the 4 new imaginary observations. So that's called the +4 estimate for P. Once you have that, you simply go through the ordinary large sample methods, but applied to the new sort of augmented data set. So the standard error of P tilde, the +4 estimate, is P tilde times 1 minus P tilde divided by the +4 sample size, right, which is N plus 4 instead of just N now. And then the margin of error is computed just as before, a critical value from the standard normal distribution times the standard error. So let's see how that works out in an example. And the example here is fairly indicative of what happens in the real world. I mean, if you're doing opinion polls, then large sample sizes are fairly routine. But if you're doing experiments, then a lot of times large sample sizes aren't really in the picture, and this is the case here. Suppose we had a random trial of a new cancer drug. And in that random trial, suppose the results were that 9 out of 16 patients treated with the new drug went into a remission for at least 6 months. Let's find a 92% +4 confidence interval for the true proportion of patients who go into remission when they're treated with the new drug. Okay, so here's the basics of the original data set. We had a sample of size 16 who were treated, and 9 of those counted as successes. Here, success just means the category you're interested in, right? We were interested in the number of people treated who went into remission. So 9 out of the 16 treated went into remission. To compute the confidence interval, we augment this data set with 4 new observations. So the +4 data would have a sample size of not 16, but 16 + 4, which is 20, of course. And as we mentioned before, in the +4 data, the 4 new observations, 2 are considered successes and 2 are considered failures. So of those 4 new data points we add to the observation, we consider 2 of them to be successes. So the new number of successes is no longer 9, but 9 + 2, or 11. Then the sample proportion of successes would be our 11 over 20, which is 0.55. We calculate the standard error based on that, right? Essentially based on this data. So that's why I'm dividing by 20 here rather than 16 when I compute the standard error. P hat times 1 minus P hat divided by the +4 sample size, which is 20. And that gives us 0.1124 rounded to 4 places. The critical value for 92% confidence is computed in the same way as before, 92% in the middle. That means 8% left over, so 4% in the left tail. We need the inverse norm of 0.96. That turns out to be 1.7507. So our margin of error then is the product of that critical value and our standard error. That turns out to be almost 20%, 0.1948. And so the 92% confidence interval computed with the +4 method here is 0.55, our p hat value, plus or minus that margin of error. So that goes about from 35.5% to 74.5%. So we're 92% confident that between 35.5% and 74.5% of patients treated with a new drug would go into remission. So that's a fairly straightforward sort of fix for the large sample confidence interval to make it accurate when the sample size is large. The book goes into the details of when this technique is applicable. Basically, as long as you have a sample size of 10 or larger, the +4 method is applicable. you might be interested, well, do I have to figure out when to go from, when can I use the large sample method versus the +4 method? Well, the fact is, the +4 method, when the sample size is large, returns a confidence interval that's essentially indistinguishable from the normal large sample methods. So a basic rule of thumb would be to use the +4 method whenever your sample size is at least 10, and you will be in good shape for getting accurate results in that case. So our last homework assignment will be over the +4 methods, and I'll get that out concurrently when I post this video. As always, let me know if you have questions, concerns, or comments. And as always, stay safe and stay well. And I will be back with you for one final video for those of you who have elected to take the final. I'll have some more information about that. Y'all take care.